I have my colleagues. I have my colleagues online, Nikita Popov and Ivan Mankov. We're working on we're a team that's doing this research. Hope you don't mind that we record this conversation because we want to get all the possible insights we can get from this.
Sure.
So just to remind you.
I think if you can share the recording, that would be great actually.
Okay, it's fine. Yeah, we'll do that. Just to remind of what we're doing, we're researching the data industry, and we're looking at the long-term horizon, like 10 to 15 years. We want to understand how this industry would look like in 10 to 15 years, and we look at the data industry, well, in a very broad way. The whole value chain from data generation to storage analysis, visualization, etc., both hardware and software. And well, I looked up your profile, and hopefully we could talk more about data storage. It's one of the areas that we're interested in. So, if I may, well, just start our conversation from the first question. I would like to ask you, how do you think the technology landscape would look like in 10 to 15 years in terms of data storage technologies?
Okay, so I think I think I do have a small picture which I can show you to you, right? That will be
Okay,
1 minute.
let me grant you the rights. Okay, did it. You can now launch the demo if you want.
Yeah. I think I can share the screen. Can you see the slides up here?
Yeah, we see that.
Yes.
Okay. Yeah. So I think I will show you. So this is the starting point of the data storage, right? From cave paintings, and slowly I'll just summarize actually. There is a summary slide also with all these kind of things. I mean, this is something really interesting picture, for the hard disk drive in 1980, more than 1 GB, and then we have all kind of floppy disks. I think some of you might have seen this CD-ROM, mod, compact flash memory, DVD, memory stick, USB flash drive. So basically now we are doing this cloud. So this picture actually summarizes really in a nice way. So you can see that right from cave paintings up to the modern cloud storage, where right now we are using actually data storage thing. So if you have any question about this slide, you can ask. I just want to keep it interactive so that you can answer any of the questions.
Yeah, well, we're not interested very much in history per se. We want to look into the future, and since I saw that, for example, you are a member of the DNA Storage Alliance,
Correct.
I think that you can comment on what could be the so-called disruptive technologies that will have a transformational impact on the industry. What's your perspective on that?
So this is a estimate given by Rick Smith in 2010 actually about how much data we are generating, right? So this is something really important. I mean, from the dawn of civilization until 2003, humankind generated 5 exabytes of data, which is 1 exabyte is equal to 1 billion gigabytes. And now we produce 5 exabytes every 2 days. This is the state in 2010. And now I think already it is a couple of exabytes every day actually, we are getting to that limit. And so, here is soon it will be in the order of 10 raised to 30. So exabyte is order of 10 raised to 18 basically, right? So now this is a really big challenge. So I think again I have a very small comparison. This, for the data you see, if you compare again, this is a bit old from year 2008. So you can see that we have terabyte for the hard disk, petabyte instead of pod. The exabyte, it required 2,000 cabinets and if you look 4-story data center.
Mm-hmm.
That takes up a city block. Zettabyte, 20% of Manhattan with 1,000 data centers, and yottabyte, will fill the estates of Delaware and Rhode Island with millions of data centers. So you see, one problem is about the space, and another problem is the cost also. This is,
Mm-hmm.
although it's a bit old picture, but it is very clear that in this picture that we have about uh, the US economy in 2008 was $14 trillion. European is $18 trillion, 14 trillion, 18 trillion, and then world GDP was $61 trillion. At that point of time in 2008, the cost of storing $100 trillion, cost of storing one yottabyte is $100 trillion. So this is something really a big challenge. And
Mm-hmm.
so why we look for a new solution now? And so new solution is ultimate storage device, which is actually, I'll show you, which is this. So 1 gram of DNA can store 455 exabytes of data. So that means, uh, again, in a very rough estimate, one can say that the size of the internet is around 700 exabytes. So basically, 2 gram of DNA will be sufficient to store entire internet, and one
Mm-hmm.
kilogram of DNA will be sufficient. 1 kg of DNA will be sufficient to store, anything ever produced on this planet in terms of information, right? So
Mm-hmm.
that is the ultimate density device we have right now. So I think, and although this started in 2012, 2013, in fact, we also did the same work, similar work in 2013 actually, and from that period, in the last 10 years, uh, it has evolved in many directions, and especially people are first looking at uh, the data that we are for archival purpose, because at that point technology is really progressing really well actually, for the archival
Mm-hmm.
purposes. So for rewritable, again, it is evolving in certain directions. Some work has been done, and still some more work is required, so that we can see the real technology in place, so that anybody can use it. So, and
Mm-hmm.
in terms of this density, there's a George Church who started this field in a seminal work. I mean, in 2012. In fact, last year, 2022, he was able to actually store about 432 exabytes of data in 1 gram of DNA. So actually, this physical density he actually achieved in the experiment also. So so on one angle, this kind of stuff is really possible in experimentally in the lab. So now it is tested. So this
Okay.
this was the theoretical limit, when now actually scientists are achieving it also.
And
But on the other hand, there are many challenges as well. So I think if you have any questions, yes, so you can ask.
yeah, what is lab you were referring to?
So our lab, we are actually, we have done the early work, because as I mentioned, in 2012, there was a first paper by George Church where they have not used any error correction for. Actually, they used manual error correction for correcting errors in the data, and they stored a certain amount of files in the DNA. Then there was a Goldman and couple of other co-authors, especially Emil from TIST Biosciences. So they did some work in 2013, and actually they use 4-4 redundancy to actually correct the errors. And we saw an opportunity that when we implemented that algorithm, we realized that it was able to encode only 500 MB file, and there was some issues if you go for higher ones. So we actually modified the algorithm, and so that it can work smoothly for any size of data. And so that was our first contribution. And after that, we did work in many directions, especially, in fact, we have also stored data in bacteria and retrieved it successfully. We have done that experiment also. So,
Bacteria.
so, yeah, bacteria. So you can use bacteria to store data actually. Okay. So that experiment also we have done. In fact, we have, so actually there are two softwares right now in our lab, which are, so one is for bacteria, another one for normal data storage, that is there. And right now we are working on some other aspects also. For example, we are working on the certain standards, So like in the DNA Storage Alliance, we are working on certain standards for archivable storage, and also for for the JPEG DNA standard also we are contributing something. So when JPG is the popular image storing standard. So when we move data into the DNA, so there also we are contributing. We have done some work there also. So how that data compression will work in the case of image. When we want to store image on the DNA, so we are doing that work also. And in fact, even for the awareness kind of thing or outreach, I think we have designed the first, to the best of our knowledge, the first course in this area actually. So last year we offered first version of the course on DNA storage and security, and this year also. So last year I think there were about 309 students who registered, and this year there are about 240 students who are registered for this course. So it's elective, where we are telling different aspects of the story, and there are many challenges. I'm saying on one hand, there are a lot of progress, but also there are a couple of challenges. Right now, in terms of both algorithms, software, error correction, all kind of stuff is going on, and also the the DNA, also the which format of DNA should be useful, and so on. There are all kind of things are going on right now.
And for this technology to be commoditized, well, the price should go down considerably. So what's the current status? As I understand, we have to, well, first of all, we have to make DNA, and then we have to sequence it. So what
Right.
is
So basically, the two bottleneck things, I think maybe I can show you another picture here. So yes. So yeah, so look at this picture here. This is a very common picture for sequence-based data storage. So the bottom bottleneck is seen as synthesis. Actually, what happens over the last 20 years or so, sequencing has become very common, and there is nanopore sequencing, which is really very efficient one for reading the data, right? But for writing data, there are three main approaches actually right now, and there are companies which are actually working on how to do this efficiently. And so these two, both synthesis and sequencing, have some cost associated with it. And I think as soon as we will have more progress in both of these technologies, this will become a common everyday technology for everyone to use actually. So these are, I mean, I think last 2 3 years, a lot more progress has been there in both of these, sequencing and synthesis. Especially synthesis is a really big bottleneck right now for the technology. So of course, I mean, you can do it obviously, but it is a bit costly right now writing the DNA. So synthetic DNA. Yeah.
I read in one article that well, the cost of this process would be like $1 per terabyte by 2030. Is it a relevant forecast or?
No, I think it will take some more time actually. Because see, actually, what happens? There are many challenges. Fagama, I should tell you that if I want to store 1 terabyte of data, so because the current writing process gives you a rough size of about 300 nucleotides, for one fragment. So basically, for 1 terabyte data, you require 1 billion fragments of DNA. Right. So actually managing all this, and all kind of issues are there actually, right? So which increases the cost also, So, if we increase how at what speed you write the DNA, that so there are many challenges actually in that case. So this will, I would say that even if it comes to $100 per terabyte, say by another 7 or 8 years, that would be more proper prediction. But actually, but things are moving very fast, and there are a lot of companies who are working in this direction, and I hope they are going to come up with a feasible, nice solution actually. But this is the thing. So the synthesis is the bottleneck right
Mm-hmm. And in your view, well, if we look at the current landscape of the data centers, which are based on solid state drives, when do you think that businesses will start replacing these SSDs with DNA storage systems?
I think probably by 2033 or 34, maybe I would say that,
Okay.
because yeah. So I think I would say roughly another 5 years. Certainly, you will see more progress. And
Mhm.
I because see what happens at some places, there are some bottlenecks, and people are working very hard, really hard to actually overcome some of those things. So once that thing is taken care, I hope within 5 years. So probably you will see maybe first data center totally based on DNA storage. Which will have
Mhm.
all kind of automated things and so on. Because the
So you
space
be-
is a beautiful thing. So as long as the synthesis, if we are able to solve this synthesis problem in a really efficient manner, we will be able to achieve that quickly. Yeah.
you believe that in 10 to 15 years the technology will become more mature and it will
Right, right.
be
Within 10
okay.
years, I would say. Within 10 years, yeah.
Mhm.
Yeah.
Nikita, I saw you wanted to ask a question. Please go ahead.
Yeah.
Yes, Professor Gupta. I'd like to ask a question. If you can name a few technologies for DNA synthesis that are currently at the level of development of maybe technology readiness level 1 or maybe 2, that you believe would actually produce a revolution in the costs of DNA synthesis and lower it significantly. So, if you have in mind specific technologies that can be used in maybe 10 to 15 years for DNA synthesis at an extremely low cost, please could you name and describe them?
Yeah, so I think if you look at the DNA synthesis process, so right now that really the chemistry based approach is what these people are using quite a lot, which is a very popular one. But I would say that enzyme based approach, which is pretty recent one, is going to lower the cost actually. So there are a lot of things are happening in that direction. So which is going to really. I think more and more work is needed, because I think it was just, I would say, just 1 or 2 year old. Where a lot more work is happening in that direction, especially from George Church Group itself, in Harvard. So I think that is going to make that will be a big game changer, especially these enzyme-based storage technique will be very, very useful actually. So, I think so. There are three popular approaches in DNA synthesis, and then enzyme-based is the most modern one actually. And I think now, I think because more and more efforts are right now in the synthesis business as compared to sequencing. Because sequencing anyway, it reaches up to the pen drive level. Now we have that kind of nanopore sequencing available to us, right? So, and there are companies right now who are working on a single combined system for both synthesis, sequencing, and everything all together in one machine, right? So I think a lot more efforts are going on in that direction, and I'm sure for the next 5 to 10 years you will see a great change in that.
Thank you so much. Thank you.
Yeah.
Uh,
Yes, I have a question. I'm not a technician or a biologist, but when I look at the data storage market, I see that there are some potentially disruptive technologies, but at the same time they are competitive. So we have DNA storage from one hand, from the other we have some potential technologies like optical storage, and we also have uh, well, some other technologies as well. So my question is, do you think that one technology would prevail over another, or this will be like a simultaneously uh, simultaneous process? Both technologies will have place in the market.
I think you are right. Optical storage is also a very nice approach for data storage, and there are a couple of other ones as well, as one of the potential candidate in the future. But one thing I believe, and of course, since I have been working in this area, of course, I have some biases about DNA storage. I see that the storage capacity, because nature is using DNA for storage, So I think, and that is probably the ultimate thing. So I think if you can actually replicate the whole thing with control in our hand, this will be the remarkable thing. Because see, with many other technologies of storage, the media decay is a big problem. So some of these things will survive for 15 years, 20 years, 25 years, whatever, 30 years. But DNA can go for 1,000 years potentially. In principle. So we have lot more potential in that area. So if you are able to actually develop the technology around DNA storage, of course there are many issues. I'm not saying that everything is solved yet, but it's moving in a very, very positive direction. So certainly I would say that DNA storage will be much more powerful as compared to the other storage. Because decay is really a big issue. And here actually we know that, I mean, you might have seen in many news and other places that people have found the DNA 10,000 years old, and they are able to recover the stuff. So I think it's really a great potential, because nature is using that actually. So in that sense, yes, I would say that DNA storage is very, very powerful.
And do you think that, well, this decay features, the DNA can last like forever, is a very critical factor for businesses?
Actually, because the decay is a big problem with all other media actually, and here also DNA is winning. So I would say that decay is one plus point for DNA, and second thing is obviously that ultimate density. These two are the very, very important factors. Because the space is less. Moreover, you require less energy to actually and also you can also say that it is a green storage. So something that is really another environmental friendly thing. That is also another very, very important point from that aspect.
And still a question, as it may sound. So DNA storage would be used only in data centers. We won't have DNA storage in like our pockets, smartphones, or any other devices. So this is a story for data centers.
So data center, see, because what I say that right now most of the focus is on archival storage, because that is easy to handle right now. So right, I think
because data doesn't have to be changed in archives.
Right. But if you look at even if you look at a data center actually, right, or even a hard disk or whatever, you see that certain portion of data it is called cold data, and certain portion is called hot data. Hot data means you require very often, and that percentage is very low, both in the data center as well as even in the hard disk. So what happens actually, for cold data, you can always use the archival technique, and for so retrieval is more or less useful for only that small portion of data. So I think apart from DNA synthesis, so this is one sequence-based approach, but the other approach, just like enzyme-based approach again for data storage in DNA, that is really very, very powerful. Of course, the density is a little bit less. For example, here if you can store 455 exabytes in 1 gram of DNA, in the enzyme-based approach, it is 30% less actually. So in that sense, actually, there are some trade-offs. But as soon as we solve the retrieval, rewritable things quite easily, then I think this will be really a boom. So I think I would say that the speed at which we are actually moving, another 10 years down the line, I could see that there will be a lot more progress by that time. Because see, even people who are interested in this area now are, even if somebody is working in the data storage industry, so the DNA is a bio thing, right? So I mean, they have to be expert in biology also, right? So all kind of expertise are required, right? So I think when more and more interdisciplinary people will attack towards the problem, and they can solve it easily actually. That I believe that. So certainly between 5 to 10 years down the line, you will be able to do it actually.
Okay. Nikita, Ivan, if we don't have any questions on data storage, I would suggest we ask a couple of questions on computing.
Yes, I have a question. So if I'm not mistaken, you say that the synthesis is the main challenge, and after that, maybe there are some issues with the speed of data retrieval. And what are the other potential challenges that you could name?
Mr. Gupta, you're on mute, I think. Can hear you.
Actually, we cannot hear you. Maybe you went on mute. Can you please switch? Maybe it was because of the phone call that you had.
Something wrong with the microphone device. Maybe it changed from AirPods to something else.
No?
Oh, for
Yeah,
now.
now we can hear you.
Yeah, so I think because of phone call, probably there was an issue. Anyway, yeah.
Mhm.
So basically, as I mentioned, even the size of synthesis, which is a challenge right now, right? So we don't have machines which can write very, very long DNA, and of course, that is also will create all other kind of problems actually, you know. So there are a lot of interportability issues as well between the current computers, and so of course we require a device which can connect to the current computer, and you can directly write down the data on the DNA and then retrieve it back, right? Those kind of devices will take another maybe 15 years or so, maybe, you know, those kind of things. But I think at some point we'll be able to find some middle solutions where actually we'll be able to do it nicely. So I think you know, certain problems. So I think it will happen slowly. So first probably archival things will happen, and then slowly towards you know, rewritable things will happen. And so, so because as I mentioned, there are many challenges. Even from the data center point of view, there are many issues are there. You know, so if you really want to replace the data center, a lot of things one has to solve before we arrive at the final DNA-based data centers actually.
Okay, and another question is, what early use cases you envision for maybe next 5 to 10 years for DNA data storage?
So I think the number one thing is archival storage, and I think already many groups who are working in that direction, you know, creating end-to-end for archival storage. That will be the easy thing to do. So,
okay. Yeah,
so
thank you so much. Thank you. Dmitry, have you heard?
Ivan, if you have questions on data storage, go ahead. If you don't,
Yep, I'm interested in one moment. How do you think will the technology will be like accessible all around, or like some companies will like try to protect their rights for this technology and keep it as a competitive advantage when it will be available?
So I think if you look at, there are two major efforts in the world right now. One is, I mean, which is visible at least to the best of my knowledge. One is so International Consortium of Storage, DNA Storage in Silicon Valley, right? But all the major companies, in fact, the storage companies as well as the other companies are working on that. You know, so there are different groups and so on. I think that's a very positive sign. I hope things are working. So all the computing companies, almost all companies are part of it, like Microsoft and other, you know, companies. And also on the other hand, like the ISO standards in Europe, like Switzerland, you know, Geneva, they are working on the JPEG DNA standards, and of course that is also open to for all public to comment and so on. So I think the, you know, more and more standards are happening, and I know there are many companies who have given many research projects in this area, you know. So I think there are many professors I know who are working in developing different kind of you know, different portions of the technology in DNA storage, right? So they're doing different portions and trying to do more and more research. So I think a lot of things are happening from the company side as well, you know, the computing companies as well. So IBM is part of it right now in the consortium. Microsoft is there, you know, and I think, I don't know, some other companies might be working something privately. So that of course we don't know unless we know, you know. So I know that Intel is also doing something actually in DNA storage.
do you happen to know anyone from Russia working on DNA storage?
Pardon?
Do you happen to know anyone from Russia who is working on DNA storage technologies?
Sorry, I couldn't hear you actually. There is some noise. Yeah.
Can you hear now?
Yeah, I can hear you now. Yeah, please go ahead.
I'm asking, do you happen to know anyone from Russia who is doing research on DNA storage?
Actually, there are obviously I know some mathematicians who are like Sasha Bug. I'm sure he is doing something. Israel, I know many people are doing actually. And there are some work going on. Sasha Berg, I know, is the one who is doing a lot more. I mean, he has earlier also contributed.
Sasha Bar? Sasha
Yeah,
Bar?
Sasha Berg, yeah.
Okay.
Yeah.
Okay,
So,
I would like to ask you about the, if we move away from, can you hear me well?
pardon?
Can you hear me well now?
Yeah, I can hear you now. Yes.
Okay, yeah, I would like to ask you about the computing architectures and how will they evolve in the next 10 to 15 years? Do you think that, for example, quantum technologies will be a game changer in the data industry, or it's a question of far away from here?
Well, actually, certainly quantum computing, as I showed you in the slides also, quantum computing, and also I think if you look at from the experimental point of view, actually, if you look at, so yeah, here is the picture you see. This is the was in 1958 with IBM computer, and this is IBM quantum computer, right? So almost the same stage. So both the technologies, as you see, 1994 was the actual time when DNA computing and the quantum computing started almost at the same time in a very positive manner. And I think in terms of storage, quantum machines, some work has been done in that direction as well. But I think a lot more work is needed really if you want to succeed in the storage part. But certainly, from the computing part, the architecture of quantum computing is going to be it's going to play a very important role, obviously. And there are many problems, for example, in the financial domain and other places where quantum computing is going to play a very important role, right? Solving certain problems in even biology or chemistry. So a lot more problems are there. So I think the quantum, from the architecture point of view, quantum computing architecture will be an important one. At the same time, the DNA computing, of course, DNA storage is one very, very specific area which is making a lot more progress. But otherwise also, because there is other architectures like chemical computing is there, So that is also another area which is very, very important, right? So there are different architectures which are evolving. So as a computing in general will be a very, very common thing. Now one can make computer out of many different things. You can also train your bacteria to do computing, right? So that is also a possibility. Okay, so different kind of computing architectures will be evolving. So all these emerging or disruptive areas, I would say. Now, which will have more potential and which will be, I think, probably some of these computing architectures will be for a specific need, right? So, for example, the quantum computer right now, we can access IBM quantum computer by remote, right? But maybe not as a common desktop computer that we see today. Maybe in future it may happen. Right now, it's very difficult to say anything about it because still there are many challenges even in the quantum computing also, right? So many things are going on. But of course, after 94, in between there was a time when it was not moving very fast because of the hardware issues. But now it is moving very fast, and a lot of things are happening in that direction.
Well, if you were to place a bet, to place 3 bets, I would say, what would they be?
In between what?
Well, in the technologies we discussed, data storage in particular, and maybe other technologies as well.
Mm-hmm.
So what are hot topics for you?
I think DNA storage is, from the technological point of view, will be very important technology, and I think that is something. And there are actually a lot of other implications in other directions as well for this technology, right? And for example, even the security, that is another very important area, right? And apart from that, I guess many other computing architectures which are emerging will play an important role actually. So, for example, even in the DNA storage, there are other kind of enzyme-based storage which is coming up in between, right? So it is changing the computing architecture even for the data storage also. So a lot of other kind of work is going on right now. Okay, so in that direction.
Mm-hmm. Okay, so we have three minutes left. I just wanted to ask you if it will be possible to for us to send you a questionnaire for you to fill. No typing involved, just clicking the answers you think are correct. We have developed a list of hypotheses regarding the future. Well, in 2035, like 20 to 30 hypotheses, and we would like to have your opinion on that as well. Would it be possible for us to send?
Okay, sure, you can send it.
So it's just a simple survey. Okay. So, guys, do you have any more questions, Professor?
No, I don't have any questions. Many thanks for your time, for the interview. It was very interesting for us. If you can send any materials, articles, academic papers that you would advise us to read through to understand the general timeline of this technology development and some future prospects, please, we would be very indebted if you do it. And
Sure.
As Dmitry said, we have a very simple survey, kind of foresight of what are the various hypotheses about the future and what are the various technologies, and I would like to have your opinion on that.
Sure, so no problem. Thank
So
you.
thank you so much.
Sure.
Thank you.
Yeah, thank you very much.
Thank
Yes.
you. Just
Have a good
send
day.
send me the recording also now so that I can.
Okay.
Yep, we will
Thank
share
Absolutely.
the link in 10 minutes and you will be able to download it.
Okay. Thank you very much. See you.
Thank you. Bye.
Okay. Bye-bye.
Bye-bye.